Okay, in this tutorial, we're looking at Leaving Cert Higher Level 2023, Paper 1, Question 4. And it's all about complex numbers. The content for Part A was covered in Complex Numbers 8. So if you want to look at similar questions, you should go to that tutorial and study it now. In this question, in Part A, we're given a quadratic. And the quadratic, the coefficient of z is not real, which means that the roots are not conjugates of each other. A really important piece of theory that we're going to use here, we studied it in Complex Numbers 8, is that every quadratic equation can be written in the form of z squared minus z times the sum of the roots plus the product of the roots. And the question in this case is actually to find the product of the roots. The product of the roots has been represented as p. But before we find the product, before we find p, we need to find the other root of this quadratic. So if I know one of the roots is 1 plus I, for the moment, let's call the other root x plus yi. It doesn't matter what letters I use there, but I'm just making it up. But all I'm saying is that the other root is also a complex number. So I want to find the value of x and find the value of y so I can tell what both of the roots are. And the way we're going to do that is using this piece here. The coefficient of z is minus times the sum of the roots. So if I'm saying that the roots of my quadratic are 1 plus I and x plus yi, I'm going to be able to figure out what x plus yi is because I know what the coefficient of z is. So let's first of all get the sum of our roots. We're going to add these together. If I add up the roots, the real values are 1 plus x and the imaginary values are 1 plus y times I. So the real bit is 1 and an x. The imaginary coefficient here is a 1. The imaginary coefficient here is a y. So that essentially is the sum of the roots. And I know that to come up with this quadratic, that the sum of the roots is equal to minus times whatever the coefficient of z is. So minus 3 minus 2i, I can let these equal to each other. And doing this, I'm going to be able to figure out a value for x and a value for y. So I'm going to do nothing with the left-hand side. The real value on the left is 1 plus x. The imaginary value on the left is 1 plus y. And on the right, I'm just changing the signs. I get minus 3 plus 2i. And I can solve this. Remember that the real terms on the left have to be equal to the real terms on the right. The imaginary terms on the left have to be equal to the imaginary terms on the right. So I can say that 1 plus x is equal to minus 3. And if I want to get x on its own, I'll just subtract 1 from both sides, and I can say x is equal to minus 4. For the imaginary values, I can ignore the i's and just take the coefficients. 1 plus y is equal to 2. Obviously, just subtract 1 from both sides, and I get y is equal to 1. So now I know what x and y are. Remember how I came up with x and y in the first place. This is the other root. So now I know that the other root of this quadratic is minus 4 plus 1i. The question gave me one of the roots. One of the roots, z1, was 1 plus 1i. And my second root now is minus 4 plus 1i. I can use this information now to get p, because p, the last term in any quadratic, is the product of the roots. So the last step here is we're just going to multiply minus 4 plus 1i by 1 plus 1i, and that's going to give me p. So the final step, I've multiplied minus 4 plus 1i by 1 plus 1i, and I get the product of the roots, which is our p. And our final answer is minus 5 minus 3i. In Part B, we're asked to use De Moivre's theorem to work out the values of w for which w squared equals minus 1 plus root 3i. The content here is very similar to what we covered in Complex Numbers 14. There's loads of examples there. So if you want to practice that, you should look at that. If you want to practice questions like this, you should look at that tutorial. First of all, you're asked to use De Moivre's theorem, so the first thing that needs to come into your head is polar form. We have to rewrite minus 1 plus root 3i in the form or cos theta plus I sine theta. Or represents the modulus, and it's calculated as the square root of a squared plus b squared, where a in this case is minus 1 and b in this case is root 3. So it's simple enough, or your modulus works out as a 2, so that's what we're going to sub in when we're dealing with polar form. Theta, the argument, is a little bit trickier. We need a diagram for that. Basically, I've drawn an Argand diagram where the horizontal line is the real axis and the vertical line is the imaginary axis. I'm going to label in -1 for the real value and plus root 3 for the imaginary value. And basically then we just plot our point. Now we form a right angle triangle. You join your point to the horizontal line and you join your point to the origin. We're trying to find the angle that the complex numbers makes with the horizontal line. And in order to do that, you should recognize the distance from here to here is simply a 1, while the vertical distance is root 3. We have a right angle triangle, and I know the opposite is root 3, and I know the adjacent is 1, so we just use trigonometry. I'm going to use tan, because I know the opposite and I know the adjacent. I can say that tan A is equal to the opposite, which is root 3, over the adjacent, which is 1. Then you can go to page 13 in your maths tables, or you can get tan inverse of root 3. Either way, it's going to tell you that the angle there is 60 degrees. But remember that that's not actually the angle you're looking for. We are looking for theta, the argument. And that is the angle that starts on the positive sense of the real axis and goes in this direction. But obviously if I know that this is 60 degrees, it's easy to work out the value of theta here. Just think of your unit circle from trigonometry and how you get a value in the second quadrant. To work out theta, it's simply going to be 180 degrees minus 60, which is 120 degrees. So now we have enough information to write this in polar form. I can say that the complex number I started off with, -1 plus root 3i, is the same as 2 times cos 120 plus I sine 120. So now that I have it in polar form, now we can discuss de Moivre's theorem. So originally we were told that w squared equals -1 plus root 3i. But now I can rewrite this complex number in polar form. It's 2 cos 120 plus I sine 120. Then you should recognize you need to get rid of the squared. So you get the square root of both sides, or in other words, you get the left and the right hand side to the power of a half. So w squared becomes w, and the right hand side becomes all of this to the power of a half. Now remember, the hardest questions we've studied in complex numbers are when you're applying de Moivre's theorem and the power is a fraction. If the power is a fraction, there are multiple answers. In this case 2, because the denominator is 2. So if your power is a fraction, the next step is you generalize your angle. So the angle 120 becomes 120 plus 360n. So again, I put in this sine 120 becomes sine 120 plus 360n. And at this stage, on the next line now, I'm applying de Moivre's theorem. You get the or 2 to the power of a half, and you multiply the angle by the power. 120 by a half is 60, 360 by a half is 180n. So this basically, at this stage I have it simplified as much as possible, and now I just need to sub in values of n to get my multiple answers. You have to recognize now that you're looking for 2 answers because the bottom of the fraction has a 2 in it. The first value you should sub in is n equals 0. If I sub in n equals 0, then obviously the 180n becomes a 0, so the angle is just 60. So I get root 2 cos 60 plus I sine 60. The cos of 60 is a half, and the sine of 60 is root 3 over 2. Then if you multiply that by root 2, your final answer works out as w equals 1 over root 2 plus root 6 over 2i. Now I'm going to just repeat these last few lines, subbing in n equals 1 to get the second answer. Now to get my second answer, I just need to sub in n equals 1. If I sub in n equals 1 into this angle, I get 60 plus 180 times 1, which is 240. So you get cos 240 plus I sine 240. The cos of 240 is minus a half, the sine of 240 is minus root 3 over 2. And if you multiply by root 2, you get your second answer, which is minus 1 over root 2 minus root 6 over 2i. In C part 1, we're given the complex number u, which is equal to a plus bi. And we're asked to come up with iu, and then the complex conjugate of iu. We've covered this kind of thing in complex number 7. Basically, we're talking about rotations here. So all we have to do for the first part is to multiply the complex number that was given by I times a plus bi becomes ai plus bi squared. And remember that I squared is a minus 1, so that means that this becomes minus b plus ai. So that's our answer for I times u. I times u is minus b plus ai. Then we're asked to get the conjugate of that, the complex conjugate of iu, which basically just means change the sign in front of the I. So minus b plus ai becomes minus b minus ai. So there are two answers for the first part of C here. Okay, in C part 2 here, we need to consider this Argand diagram. In the Argand diagram, they've plotted the coordinates, they've plotted the complex number a plus bi. You should recognize that a corresponds to the real value, so if it's that far out from the vertical line, I know that the distance from here to here must be a. So I could say that that's a. And I can also plot here that the b, the coefficient in front of I, corresponds to the vertical axis. So I could say that that's a b. Now in my head here, I'm pretending that a is 1 and b is 4. It looks to me like that distance is about a quarter of the distance b. A is the short one, b is the long one. And the question is asking you as accurately as possible to plot IU and the conjugate of IU on the same diagram. So for IU, the real value is minus b. So that minus b, obviously, that's a real value, so it has to go on the horizontal line, and I want it to be roughly that distance. So if I was guessing, I'd say, there's my minus b. And I also need to figure out where the a is. A is on the imaginary axis, so I want to go about this distance up the imaginary axis. So let's say that that's a. So now I can plot the point, or the complex number, minus b plus ai. Minus b plus ai is roughly there, and that I will label it as IU. Likewise, we need to plot minus b minus ai. So minus b, I already have that. Minus ai means I need to go this distance on the imaginary axis. So let's say that roughly looks like it's the same distance again. So I can label this as minus a. And then, since I don't need that minus b, I'll get rid of it. I can plot in here, this is minus b minus ai, and that is IU. That is the conjugate of IU. In the final part of this question, we're asked to state a series of transformations that would allow us to move u to the conjugate of IU. So the easiest way I think to look at this is that we should do two transformations. First of all, what do we have to do to move u onto IU? And then what do we have to do to turn IU into its conjugate? Thinking of transformations. If you're rusty on this, the last thing we studied in geometry, if you look at the second last video, we discussed all of these different types of transformations in geometry. Now, the first thing you have to ask yourself is, how do I turn u into IU? In complex numbers, it requires just multiplying by I, and we know that that is a 90-degree anti-clockwise rotation. So to go from there to there, it's a 90-degree anti-clockwise rotation. Essentially, you're just moving it one quadrant in an anti-clockwise direction. So it moves over to this quadrant. So it's a 90-degree anti-clockwise rotation. And it's important you use the word rotation there because the rotation is the actual type of transformation. Then how do we go from IU to its conjugate? Well, in this case, it's axial symmetry. Remember, axial symmetry is, imagine if I folded this over. Imagine if I folded the top diagram over along the real axis. If I folded this over the real axis, it would fold over here. Imagine if this was a piece of paper and I folded along this line, then IU would move to the conjugate of IU. So the second thing you would do then is axial symmetry in the real axis. So they're the two, axial symmetry in the real axis. So they're the two transformations we'd have to do to move u onto the conjugate of IU. And that's all you need to write down to get the marks for this question.